This is a lecture on optimization. We are going to look at what's called our second derivative test for maximum and minimum. This is important because what this allows us to do is simply calculate our first and second derivative without ever having to actually sit there and graph the function, which is very important. Your second derivative test depends on, first and foremost, that your first derivative is 0. If your first derivative at a point is 0, then we take the second derivative. And if the second derivative at the second point is that same point is less than 0, then there's a maximum at that point. And if the second derivative is greater than 0, then there's a minimum at that point. Let's think of this visually. Here we have some graphs. Notice that this graph, if we look at this point down here, this point, the first derivative is 0. Notice there's a horizontal tangent line. And what we notice about the second derivative is concave up, which tells us the second derivative is positive, which means this is a minimum. So if I have a situation where the first derivative of a point is 0, and the second derivative is positive or concave up, then that tells me I have a minimum at this point. Conversely, if I have a situation, like I do on this right-hand side, where the first derivative is 0, and the second derivative is negative, then what this tells me is I have a relative maximum at that point. Again, this is helpful in the fact that we only have to calculate the first and second derivative. We don't necessarily have to graph it, but this is why this works. Again, the reason we want to do this is that when we do problems, and we're going to be getting to some of these today with optimization, is we don't want to have to graph every function we come across, but we do want to find out where our relative max and mins are. Let's look at an example of this. For what value of x does the function f of x equals 5 plus 6x minus x squared have its maximum value? Whenever we hear maximum and minimum, our mind should automatically think derivatives. We take our first derivative of this function. We get f prime of x is 6 minus 2x. We do know that the key here is setting our first derivative equal to 0 because our maxims and mins always occur where the first derivative is 0. We set it equal to 0, and this gives us x equals 3. This is really nice because this tells us we have a critical point. However, it doesn't tell us if it's a maximum or minimum. If we turn around and calculate the second derivative, we find out from the first derivative the second derivative is negative 2. This tells me the second derivative is negative everywhere, so it's concave down everywhere. Therefore, x equals 3, I can now classify it as a maximum. I already knew it was a critical point because the first derivative was 0. Now that I know the second derivative is negative, I can classify it as a maximum. So this function obtains its maximum value at x equals 3. Here's another example. For what value of x does the function f of x equals 6x squared minus x cubed have its maximum value? Again, our process is the same. We take our first derivative, which is 12x minus 3x squared, set this equal to 0. In this case, we're going to factor. And we wind up with 0 and 4 as critical points. Now we don't know whether either of these is a maximum or a minimum. So what we're going to do is take our second derivative. Our second derivative gives us 12 minus 6x. Now notice this isn't always positive or always negative. What we have to do is we have to plug in each one of our critical points. We'll first plug in x equals 0. At x equals 0, we get the second derivative is 12. And at x equals 4, we get the second derivative is negative 12. We already know both of these x values, 0 and 4, make our first derivative 0. However, 0 also makes our second derivative positive, so this tells us x equals 0 is a relative minimum of the function, and this tells us x equals 4 is a relative maximum because the second derivative is negative, which tells us it's concave down. Now, why is this important? This is very important when we're doing optimization. Optimization wants us to find the largest or the maximum or the smallest or minimum quantities. This involves taking derivatives. Now, when we do optimization, we're often given constraints to our equations. In other words, we have limited resources, limited dimensions, things to that effect. So what we're going to do this is a series of steps to calculate our relative minims and maximums or our optimizations for these problems. What we're going to do is we're going to get two equations. We're going to find an objective equation, which is the equation we're trying to optimize. In other words, find the largest or the smallest value for it. And we're going to use a constraint equation. And basically what this shows is the limits of what we have or can use. Now what we're always going to do is we will always plug the constraint equation into the objective equation and optimize the objective equation. Let's see how this works through an example. There are $480 available to fence in a rectangular garden. Due to an HOA restriction, the fencing facing the front of the property costs $18 per foot, but the fencing for the rest of the garden is only $6 per foot. We want to find the dimensions which give us the largest area. Our steps are quite simple. First, we're going to determine the objective and constraint equations. We'll talk about how to do that. Second, we're going to express the quantity to be maximized as a function of x. And finally, we're going to find the optimal values of x and y. Here's a sketch of it. We have a rectangular garden. The front fencing is $18 a linear foot. The rest are $6 a linear foot. Notice the front and the back have the same x measurement, and the two sides have the y measurement. We need to find the objective equation. Remember, the objective equation is the one that's going to be optimized, and optimization means max or min. If we look at it, the last part says we want to find the dimensions which give us the largest area. Largest is clearly what we want to maximize, so we want to maximize the area. And if you look at this, this is a rectangle, so the area of a rectangle is length times width, or in this case, just x times y. Now we are given a constraint. We do have a budget. We can't spend more than this budget. You know our dimensions are x and y. The front fencing is going to cost us $18 times x feet. The back fencing is going to cost us $6 times x feet. And the two side fencings are going to cost us $6 times y feet. So our constraint is 480 times the cost for each side. 6 times y plus 6 times y plus 6 times x plus 18 times x. I can simplify this to 480 equals 12y plus 24x. I'm going to go ahead and solve for y here. One of the reasons we can do that is looking ahead. It tells us to put the constraint equation in terms of x, which means I want to get rid of the y. I want to put the objective equation in terms of x, which means I want to get rid of the y. And the way to do that is to solve for y in your constraint. So y is 40 minus 2x. Our next problem is to express the quantity to be maximized as a function of x. Again, there's our objective. Area is x times y. Our constraint is y equals 40 minus 2x. Remember, your objective equation is always the one you want to optimize. So what we're going to do is we're going to put this in terms of x. So a as a function of x equals x times 40 minus 2x. Notice I wrote this because I wrote the x to write it as in function notation. On the right hand side, all I did was replace the y with the constraint. Y is 40 minus 2x. Now I'm going to simply simplify it. Area is a function of x. A of x equals 40x minus 2x squared. The last part says find the optimal values of x and y. Well, here's our equation. To optimize it, we need to find the maximum. So we're going to take a derivative. A prime of x is 40 minus 4x, which is 0. If we solve this, we will find out that our critical point occurs at x equals 10. Now again, we only know it's a critical point. We don't know if it's a max or a min, so we'll take the second derivative. The second derivative is a double prime, which is negative 4. This tells us it's a maximum because it's negative everywhere. Now, I know the x value. I still need the y value. We're going to take our constraint equation, one of our original equations, and we're going to plug back in 10 for x, which gives us 20 for y. So our maximum area occurs when x is 10 feet and y is 20 feet. This will give us the greatest area for the garden based on our budget. There's another similar problem here. This one's very subtly different though, and it's very important that we understand the distinctions between the objective and the constraint equations. This one reads a rectangular garden of area 680 square feet, has a brick wall on one side which costs $12 per foot, and on the other three sides by a wood fence costing $5 per foot. Find the dimensions of the garden such that the cost of the materials is minimized. Same three steps, getting our objective and constraint equations, expressing the quantity to be maximized as a function of x, and then optimizing the values of x and y. Now this one's subtly different. The objective is what we want to optimize. Notice here, we want to minimize our cost. Okay? This is different than what we had before. Before we wanted to maximize the area. So our equations are actually going to be reversed in this case. Our cost function, we have 12 dollars per foot for x feet, $5 per foot for x feet, and two sides at $5 per foot for y feet. So our cost is 5y plus 5y plus 5x plus 12x, which reduces to the cost is 10y plus 17x. Now our constraint equation is we're told we want a rectangular garden of area 680 feet. Now some of you may say, well, why do we need to restrict area? Doesn't it seem weird to restrict things? Not necessarily. If you're in farming or in agriculture or you're raising livestock, sometimes you need to grow a certain amount of crops. Sometimes if you have, say, cows or horses, they each need a certain amount of area to thrive and survive in. So sometimes the area is the key. Our constraint is our area equation in this case. Area is length times width. So 680 is x times y. So again, I'm going to solve for y because I know my second step is to put it in terms of x. So y is 680 over x. Again, the second part says is to express the quantity to be maximized as a function of x. There's our cost function. There is the constraint, y is 680 over x. Now I'm going to plug this y into our cost function. So c of x is 10 times 680 over x plus 17x, which is just 6800 over x plus 17x. This is where I'm going to do a little bit of trick here. This isn't something you have to do. I find it much easier to do. I'm going to factor out a 17 here. The reason I can do that is that clearly the 17x is divisible by 17, but the 6800 also happens to be as well. So our cost function is 17 times 400 over x plus x. The reason I do that is when I go to take derivatives, it's easier to take the derivatives of terms with smaller numbers. Again, my next step is to optimize. I have to take the derivative of 400 over x plus x. Derivative of x is clearly 1. Derivative of 400 over x, remember we can rewrite this as 400 times x to the negative 1 and use our power rule. So this is going to be, our constant out front comes down, 17. This is negative 400 over x squared plus 1 is 0. When I set this equal to 0, I know that 17 is never equal to 0. So I need to find out when negative 400 over x squared is equal to 0. This occurs when x squared is equal to 400, because clearly this term has to be equal to 1, and this is only equal to 1 when the numerator and denominator are the same. Now when you take the square root of this, you get x is 20. Now clearly we could get negative 20 as well, but we know we can't have a negative measurement, so we went ahead and eliminate that. So I know that my first derivative is 0 when x is 20. Again, I need to worry about my second derivative. So we're going to take our first derivative, take the derivative of that. The derivative of 1 is 0. Then I've got to take the derivative of negative 400 over x squared. This becomes 800 over, that's supposed to be an x cubed. I apologize for not getting that fixed. 800 over x cubed. Now, when I plug in the 20, again a cubed, 17 is positive, 800 is positive, 20 is positive, so it's all positive, so it's greater than 0, which means it's a minimum. Now I need to take this 20 and plug back into my constraint equation. You get 680 over x, so y is 34. So our minimum cost occurs when x is 20 feet and y is 34 feet. If you remember marginal cost was simply the derivative of the cost function. And this gave us an estimate to produce the next item, i.e. n plus 1, given that we already know the cost to produce n items. Here's a classic example. Given the cost function, c of x equals 4x cubed minus 2x squared plus 4x plus 9, find the minimal marginal cost. This one is an interesting question, and it's interesting because of the way it's written. If you'll notice, we're given the cost function, not the marginal cost function. To calculate the marginal cost, we first have to take the derivative of the cost function. So c prime of x is 12x squared minus 4x plus 4. Nothing earth-shattering about this, but we need to kind of change the way we think, because typically, to date, to optimize something, we take the first and second derivative. Well, what we're doing is we're already starting with the first derivative. So to take the first and second derivative of the marginal cost function, what we're going to wind up doing is basically taking the second and third derivative of the original function. Here's our marginal cost function. Its first derivative is the second derivative of the original function. So c double prime of x is 24x minus 4. This means that at setting this equal to 0, we get a critical point at x is 1/6. Now, again, typically you're like, well, wait a second, this is our second derivative test. It's the second derivative of the original of whatever function we're trying to optimize. This is the first derivative of the marginal cost function. Again, a little bit convoluted, but stop and think about it. We didn't start with c of x, okay? We had to take the derivative and start with c prime. So even though this says c double prime, this is still the first derivative of the marginal cost function. We're going to take the second derivative of the marginal cost function, which is really c triple prime, and this gives us 24. So this tells us we have a minimum marginal cost at x equals 1/6 because the first derivative of the cost function was 0 at x equals 1/6. Second derivative of the marginal cost function was positive everywhere, so that tells me it's concave up. Minimum marginal cost. Now what I have to do with this is to actually find the minimum marginal cost. I need to plug back into the marginal cost equation. I'm going to plug 1/6 in for x. Then I'm going to simplify, and this is going to give us $3.67. So our minimum marginal cost is going to be $3.67. Let's get into a few more things dealing with business equations. We have something called our demand equation, which is little p equals f of x. This is what's going to give us the price at which we're going to set things. Now typically, as price increases, demand decreases and vice versa. This price function is a little bit different though, because this price function is going to be input of units and output of dollars. This price function, little p, is also going to help us determine our revenue equation, which we'll get to in a second. Typical demand functions look like this. They're inverse relationships. As x increases, y decreases, and vice versa. As x decreases, y increases. This is the classical we're going to study on the right. This is p equals mx plus b. P is just our y value. This is our price. It's dependent on the slope, the rate, times the number of units sold, plus our y-intercept. Let's look at an example of this. Till recently, hamburgers at a local eatery were $2.90 each. They sold on average 110 per night. When the price was raised to $3.50, their average sales dropped to 50 per night. Assume a linear demand curve. Find the actual demand function P for hamburgers. Well, if it's linear, we know it's going to look like this. P equals mx plus b. And we know this is a linear equation, so we always need two things for a line. We need a point and a slope. Well, the way these are written, these are actually points. At 110 per night, it costs $2.90. And at 50 per night, we sold them at $3.50. So we have 2 points, 110, 2.9, and 50, 3.5. Let me stop for a second and just point out, this almost seems like this should be backwards, that the price should drive the sales, but the price is the actual output, the function. So we need to make sure we keep our x and our y values the same. Now that we have 2 points, we can calculate a slope. Your slope's change in y over change in x. We do the quick arithmetic, we find out our slope is negative 0.01. Now, we need to find an equation for a line. We don't have the y-intercept because we'll notice neither one of our inputs are 0. So we're going to plug into our point slope formula. Y minus y1 equals m times x minus x1. It doesn't matter which point we're going to use, so let's pick the 50, 3.5. We get y minus 3.5 is negative 0.01 times x minus 50. We're going to solve for y, and in the end we're going to replace y with p. So our price function, our demand function, p equals negative 0.01x plus 4. We're going to come back to this example here at the end of our lecture, but this is what we're really trying to get at when we have a linear demand curve. Now revenue is a fairly simple concept. Your revenue is units sold times the price per unit. So if something costs $100, you sell 200 of them, your revenue is $20,000. Put it in terms of what we already know. R of x is x times p. This is x units times the demand. And remember, your demand just measures the price. You have what's called a cost function. Your cost function is your variable cost per unit times the number of units sold plus the fixed cost. Your fixed cost is usually your overhead. So your cost function is typically written mx, c of x equals mx plus b, where m is your variable cost and b is your fixed cost. Let's go back to our hamburger examples. What is the cost function for a restaurant selling hamburgers if the variable cost per hamburger is 60 cents and the fixed cost is $2,500 per night? Well, again, your cost function is just C of x equals mx plus b. M is your variable cost, which is 60 cents per burger. B is your fixed cost, which is $2,500. So C of x is 0.60x plus 2,500. Your profit function, profit's simply revenue minus cost. How much money did you bring in minus what were your costs? So P of x is R of x minus C of x. That gives us all our basic equations. Now we need to work on optimizing these equations. A few years ago, the demand for copper was approximately satisfied by the equation P is 298 minus 30x. And the total cost of producing x units of copper was C of x equals 178 plus 58x, with x in millions of tons and C of x measured in millions of dollars. Determine the level of production and corresponding price that will maximize profits. This is actually a fairly complex problem because we need to work out several things. Remember, we're maximizing profits. So to get maximum profits, we need the revenue function and the cost function. So the nice thing is we already have the cost function. We don't have the revenue function, but we do have the demand function. So we're going to start with a series of steps. We're going to calculate the revenue function, R of x. Then we're going to calculate the profit function, P of x. Then we want to differentiate the profit function to find the maximum, because it did ask us back here for the level of production and corresponding price that will maximize profits. So we're going to start. R of x is x times P, and remember P is demand, so x times P. P is 298 minus 30x. So our revenue is 298x minus 30x squared. Fairly simple, fairly straightforward. Our second thing is to calculate the profit. Remember, your profit is P of x is R of x minus C of x. We just calculated the revenue on the previous slide, so there's our revenue function, 298x minus 30x squared. And we were given our cost function of 178 plus 58x. So we're going to subtract the two. And our profit function is negative 178 plus 240x minus 30x squared. Again, we want to do our next step, which is to maximize or optimize P of x. Here's our profit function. To maximize it, we need to take the derivative. We get 240 minus 60x. We set this equal to 0 and solve. We get x is 4. Again, we know this is a critical point. We don't know if it's a maximum or a minimum. The second derivative tells us P double prime of x is negative 60. So x is 4 is a maximum. So 4 million tons is the amount we need to produce to maximize our profits. And the maximum profits will give us 302 million. So the maximum profits of 302 million occurs when 4 million tons are produced. Our last example is maximizing revenue. Remember our hamburger example said until recently hamburgers at a local eatery were $2.90 each. They sold on average 110 per night. When the price was raised to $3.50, their average sales dropped to 50 per night. Assume a linear demand curve. Find the price of hamburgers and will maximize revenue. Well, again, a linear demand curve. We already calculated that on the previous slide. Go back earlier in the lecture. We found it was negative 0.01x plus 4. So that is our demand curve. Our revenue is x times P. And if we plug in for P and x, we get negative 0.01x squared plus 4x. And I want to maximize this revenue. So I'm going to take the derivative. I get negative 0.02x plus 4. And that tells me x is 200. Again, this is just a critical point. So I take the second derivative. I get negative 0.02, which is less than 0 everywhere. So therefore I know x equals 200 is a maximum. And what is the actual demand? Because it says assume a linear function, find the price of the hamburger. Well, the sales of 200 will maximize the revenue. We can plug back in and find the maximum revenue, but it asks us to find the price. So I'm going to take my demand function, P equals negative 0.01x plus 4. I'm going to plug 200 in for x, and the price is $2. So charging $2 per hamburger will maximize the revenue. Please, before we end here, realize that maximizing revenue and maximizing profit are two different things. and make sure you're using the appropriate equation to get your maximum.